Hello, everyone. Thank you for being here. I'm Melissa Maribel. If you are new to this Q&A, I do this every single Sunday. I'm your personal tutor, and I'm here to help you guys pass chemistry. So thank you so much for being here. Wow, we have so many questions already. That's amazing. I'll go ahead and start with the first one, and then everyone, just in case you're new here, pretty much how this works is I answer one question per person, just to be as fair as possible, since I know there are so many people asking questions. And then another thing is, if you have a specific question rather than just like a generic topic, like let's say stoichiometry, I would much appreciate you actually sending in or, putting in the chat the actual specific question or example, just so I know exactly where you're struggling, and then we can, move along through all of these examples. All right, guys. So one more little thing I wanted to mention was we're getting closer and closer to 10,000 subscribers. And one of my big goals this semester was to hit 10,000 subscribers. And if we get there, and if you guys can help me out with that, I'd be great. I'd really appreciate it. I would do an 8-hour live Q&A. So I can tell you guys love these Q&As. So to help you guys with tests or finals that are coming up, please share my videos, tell people who may benefit from these, chemistry tutorials overall. That's exactly what I would, want to do, is I want to help you guys just pass chemistry and understand all this. So once again, if we hit 10,000 subscribers, I will do an 8-hour live Q&A. All right, guys, let's go ahead and start with the first question. So Kali is asking, why is the pressure inside a balloon, as it gets smaller, contain less pressure than its atmosphere? Okay, so we're really looking at atmospheric pressure in this case, and let's draw a balloon and let's think about this. So what happens if we have a balloon in our hand, right, and then we release it, and then it magically just floats away? What's eventually going to happen to it? So think of it this way. We have a balloon. All right, some art skills here. All right, we have a balloon, and essentially what's happening is, yes, there is pressure within this balloon already, and I'm just going to say this is the pressure of our balloon. And then what's happening essentially is that if we have pressure in that balloon, there are gas molecules that are kind of bouncing around and just going and are within that balloon. Okay, so we have those molecules. Now, the other thing that we don't typically look at is the actual atmosphere, or the air that's kind of being pressed on that balloon. So think of it as there is atmospheric pressure that is pushing down on that balloon, and that's why eventually it will get smaller and smaller, and essentially that's why you have less pressure inside the balloon than in the atmosphere. Think of it also this way: inside the balloon, you think of it kind of like a container, right? We're containing that air or that pressure within that balloon, yet the atmosphere is so large and we're not able to contain it per se. So that's why the pressure inside the balloon is going to get smaller and smaller as we kind of go higher and higher in the atmosphere, because our atmospheric pressure increases. That's the concept. All right, let's go to Morgan's question. So Morgan asks, calculate the total pressure. Okay, so we're looking for total pressure, and we are given 12.2 liters of a vessel that contains 2.34 grams of C2. I'm assuming C2. 1.73 grams of SO2 and 3.33 grams of argon. And then we're also given a temperature. Oh, you meant CO2. Okay, thank you. Perfect. And then that's helpful. And then our temperature is 42 degrees Celsius. And we want our pressure to be in millimeters mercury. What is the partial pressure of each gas? Okay, so two different questions in this case. So the first thing that I'm going to look for is just the total pressure, because to figure out the partial pressure of each gas, we need to first figure out the total pressure. So what I'm going to do is I'm actually going to use the ideal gas law. And what I want you to think of here with the ideal gas law Typically, it's PV equals nRT. But in this case, because this is a gas mixture, since there are multiple gases within, I want you to think of this as instead of just P, it's going to be our total pressure that we have. And then we're still going to have the volume. That's what they gave us. Our moles would have been the total moles. So we will have to convert each one of those grams to moles, add them all together, and that's going to give us our total moles. We'll do that in a second. And then R, just our typical gas constant, and then temperature in Kelvin. So let's go ahead and convert everything. What I'm going to do first is just figure out how many moles we have of everything. Let me grab my periodic table. All right, so let's start off with 2.34 grams of carbon dioxide. We'll use the molar mass of carbon dioxide, and it's roughly 44.02 grams of CO2. It's just one I've seen so many times that I have memorized by now. And then I'll divide those two, and that's going to give us the amount of moles. So we have 2.34 divided by 44.02, and we'll get 0.053 moles of CO2. I'm going to do this for every single one of those gases. So we also have 1.73 grams of SO2. All right, now this one I don't have memorized. So this is 1 mole of SO2, and let's figure this out together. So figuring out our molar mass, sulfur has a molar mass of, let's check. So sulfur has a molar mass of 32.06. Oxygen is 16 times that 2. So 32 plus this additional 32. So we'll have 64.06 grams of SO2. I'm going to divide those two to get our moles. 1.73 divided by 64.06. All right, and our moles here are 0.27 moles of SO2. And then from here, lastly, I'm going to change those grams of argon, so 3.33 grams of argon. Finding the molar mass of that on the periodic table, it is 39.95 grams per every 1 mole. And we'll once again divide those two. So dividing these two, we have 3.33 divided by 39.95. This gives us 0.0833. Actually, I'm going to round up. This would have been 34 moles of argon. Okay, so what I'm doing first is I'm trying to calculate what the total amount of moles are. So since I changed everything to moles, now I'm just going to add them all together. So the moles that we found initially for carbon dioxide was 0.053 moles of CO2. I'm going to add that to the moles of SO2 that we found, and that was 0.027 plus the moles of argon. Okay, so let's add all of those together and see what we get. 0.053 plus the 0.027 plus that 0.0834. And then our total amount of moles is this value. And then one more thing to do, we have to convert our temperature to Kelvin. So our temperature was initially 42 degrees Celsius. I'll add 273, and that'll convert it to Kelvin. So this would have been 315 Kelvin. Okay, now what we'll do is we'll plug everything in to our ideal gas law, but this version of our ideal gas law in here. This is our total, our gas constant, and our temperature. And what I'm going to do, I'm just going to actually change this formula just a tad and divide over that volume so we can solve just for our total pressure and then really just plug in. So at this point, I'm just going to plug everything in. Our total pressure, our total moles were the 0.1634 moles. And then on top, I'm going to have that R, or our gas constant, which is 0.0821 liters atmospheres divided by moles Kelvin. And then let me keep going with this. Then from here, we're going to have our temperature, which was 315, because that's in Kelvin. And lastly, our volume is on the bottom, 12.2 liters. Our total pressure, let's figure all of this out. We'll multiply straight across on the top. And we'll see what we get from that. And then I'm going to divide by 12.2. and our total pressure is going to be 0.346 atmospheres. This question asked for millimeters mercury. So one last step there is I'm going to convert this. So converting this to millimeters mercury, in 1 atmosphere, there are 760 millimeters mercury. Multiply, and we'll finally get our total pressure. So multiplying these two together, we'll get 263 millimeters mercury. So that's for that first part. And then for the next part, running out of a little bit of room here, but what you would do next is you can do this. So since you want the partial pressure of each gas, so let's say of our partial pressure of CO2, I'll show you how to do it for one, and then you'll be able to actually, replicate it. Really, the formula that you're going to use here is, this is the partial pressure formula where you're going to multiply your mole fraction, and I'll show you how to do that. So mole fraction times the total pressure. So in this case, what a mole fraction is, so let me show you how to get that mole fraction. A mole fraction is the amount of moles of whatever you're looking for, like in this case CO2, divided by your total moles. So luckily, we really found our total moles. So let me go back and figure out what was our total moles. 0.16 here, 0.1634. Okay. So what I'm going to do is I'm going to plug in all the values that I already know. So 0.1632 or 34 is our total amount of moles. Our moles of CO2, we found those as well. So we found those to be, let me go back, 0.053. All right, a long question. 0.053. And then we'll divide these two values, and that's going to give us the mole fraction of CO2. And then lastly, I'll multiply that by the total pressure, and you're going to replicate that for each one. So this would have been here, 0.053 divided by 0.1634. That would have given us 0.324. And then mole fractions don't have any units. And then in this case, finally, that we found our mole fraction, I'm just going to plug that into the formula. This is the partial pressure of CO2. So I'll multiply that mole fraction that we just found times the the total pressure that we found before, which was, let me go back, that was 263. 263 millimeters mercury, and that'll give us our partial pressure of CO2. 0.324 times 263. This is 85.2 millimeters mercury. So that would have been our partial pressure of CO2. You're going to do the exact same thing for all the others. So instead of CO2 here, you would have done SO2, and you would have found the mole fraction of SO2 as well. So here, all that's going to really change is pretty much just this part, okay? Where since this is SO2, you're just going to put the moles of SO2 that we found, still divided by the exact same total moles. That's not going to change. It's just this top value that's going to change every single time. Then once you divide those two and get whatever value you would have gotten, you then multiply by the same total pressure, which is at 263. And then you do the same exact thing for argon as well, just changing this again. Okay, so that's the main concept. It's really the same exact thing, just different numbers. All right, I'm going to move on to Rebecca's question. And let me erase all this. Let me see if I can zoom in a little bit. Okay. All right, so our question from Rebecca says, can you go over the zero order, first order, and second order rate laws and their graphs? Sure. So when we're looking at zero order and really just kinetics in general, so here we're going to have a zero order, and I'll write down what the typical rate looks like and then what they're dependent on. So let's say for zero order here, your rate law is going to be equal to RK. And then this A value is really just talking about the concentration of our reactant. And I'm just kind of, generalizing that. So A can be any sort of reactant. And then it's raised to the 0 power. We know anything to the 0 power is 1. So that really goes away. And then our actual rate is just equal to K. So zero order does not depend on the concentration of reactant. So think of it as if we were to double, triple, really increase our concentration of our reactant, that does not affect the rate law or doesn't affect the rate whatsoever. So that's the main thing with zero order. And then what you would see for your graph, here, let me draw that to the side. So what you would see for your graph, it's going to just be a constant line. So nothing's changing because it doesn't, and here, remember that the x-axis is the concentration of your reactant, and then your y-axis is just the rate. So that's why it's completely constant, nothing's changing. And then let's say for first order, it does depend on the concentration of your reactant. Actually, all the other rates or orders do. So for first order, you would see your rate is equal to K, and then the concentration of our reactant raised to the first power, just signifying the first order. And then think of this as being a bit proportional to each other, just meaning as we increase our concentration of our reactant, we are thus increasing our overall rate. So this is a bit more consistent or a bit more constant. So the fact that I'm saying they're proportional, what I want you to think of is a straight line. That's essentially it, okay? Their graphs is just going to be a constant straight line. So that's what we would have, and it does have a slope. And then next, our second order. So our second order is a tiny bit different, nothing too much. It's just increasing at a faster rate. So this is where we would have this sort of rate, right? Has a little 2, just signifying second order. And then think of it this way. If we were to, let's say, double our concentration of our reactant, then our rate will quadruple. That's the main thing to look at it. Another little hint there is the fact that this is squared, right? So how this is going to be, it's going to be an exponential curve. So it's increasing at a faster rate. Once again, this is our rate. This is our concentration of our reactant. So those are all of the orders and all the graphs as well. Hope that makes more sense, Rebecca. And next we have a couple, actually we have the same titration questions from 2 different people. Cool. All right. Well, I'll answer it. So Saban says we have, here, let's go over those titration questions. So we have 2 milliliters, 12.0 milliliters of 0.70 acetic acid. And this is, it should have been molarity. Yeah, molarity of acetic acid was titrated with 0.10 moles divided by liters of barium hydroxide. What is the titrant? And sketch the titration curve indicating the shape of the curve and the equivalent pH value. Got it. Okay, so what we're going to do first is we're going to try to figure out what is the equivalence point. So meaning how many milliliters will it take for our barium hydroxide or our strong base to completely neutralize that weak acid, which is acetic acid. So that's actually what I want to look at. What we have to do first is build a balanced reaction. So that's what we're going to use. It's going to be a bit of stoichiometry here. So let's start off with just writing out acetic acid's formula, and let's go from there. So acetic acid would look something like this. Acetic acid or acetate, here, I'll write that here. Looks like that. We know it's an acid. That's why there's an H in front. So acetic acid is going to look like a 2. It's going to look like this. Okay. And then next, I'm going to add that to our strong base. So barium hydroxide. And then this will produce, anytime we have an acid and a base, or really a neutralization reaction, we're going to produce a salt and water. So in our case, what we would have produced, essentially just think your salt is going to be the barium and the acetate combining together. And then think of it as barium has that 2+ charge, acetate just has that 1-. And then this has to be balanced. So I would have put barium, parentheses, our acetate, and then a 2 subscript. And then water will just be produced afterwards. Okay. So far that's what we have. We'll double check, is this balanced? Because it's not. So let's go back and balance this overall reaction. Okay. Balancing this reaction, I'm just going to start with how many hydrogens do we have, and then I'm going to keep acetate intact, and then I'll have barium on the side, and then oxygen also from that OH part. All right, we'll do this together. Okay, so how many hydrogens do we have overall? Well, there's one. I'm not going to touch the ones that are within the acetate ion, and then this is just one, so there are 3 here because of this 2. So far we have 3 hydrogens. On the opposite side, we only have 2. For acetate here, there's only 1. And for acetate here, there are 2. Okay, and then next barium would have been 1, and then barium here would have also been 1. Oxygen, let's see what that would have given us. Here, let me highlight that. So it would have been 2 on this side, and then there would have just been 1 on the other. Okay, so what I want to balance out first, let's start off with the acetates. So what I'm going to do is I'm going to put a 2 in front here, and that's essentially distributing. And what I'll do is I'll recount everything. So we have 2 acetates, we have 2 plus that additional 2, so giving us 4 hydrogens, and then everything else remained the same. Next, I have to balance out the product side, and because we don't have the correct amount of oxygen or hydrogens, so I'm just going to put a 2 in front, and you'll notice everything's balanced now. So this is a 4, and this is a 2. Everything is good. Okay. So that's the correct balancing. Now that we got that down, let's actually do the math. So building our stoichiometry problem here. Let's make this a tiny bit cleaner. There we go. Okay, so let's start off with what we had initially. So what I'm going to use first is I'm going to start off with the 12 milliliters of acetic acid. So starting with 12.0 milliliters of acetic acid, and then I'm going to convert this to liters just so I can use that molarity that was provided as a conversion factor. So on the bottom, I'll have 1,000 milliliters per every 1 liter. And then this is still of acetic acid. And then what I'm going to do next is I'm going to use that concentration or that molarity that was provided, that 0.70. And how I'm going to use it is there's really 1 liter on the bottom with molarity, right? We know molarity is equal to moles divided by liters, and then on top would be 0.70 moles of acetic acid. So HC2, all right, all of that. And then from here, I'm trying to figure out how many milliliters are being used with our base of barium hydroxide. So I want to do a mole to mole ratio. I'm going to multiply this, and we're going to put our moles of acetic acid on the bottom, and then on top we want the moles of barium hydroxide. Okay, and then I'm going to go back and let's see how many of each we have. So there are 2 moles of acetic acid per every 1 mole of barium hydroxide. So on the bottom, there are 2 moles and 1 mole of barium hydroxide. Next, we were also given the molarity of barium hydroxide, so I'm going to use that now. And then what you're actually going to do, you're kind of going to like flip it. Instead of putting the moles on top, you're going to put them on bottom. The reason we're doing that is so it can cancel out with these moles right here. Okay, so then I have 10 moles of barium hydroxide. And then on top, I'm just going to put that 1 liter of barium hydroxide. Last step is to change this to milliliters. Changing this to milliliters, think of this as 1,000 milliliters per every 1 liter. This is still barium hydroxide, and this will finally tell us what the equivalence point is, or how much we need. And then we'll get to the pH in a second. Okay, so let's start off with just multiplying everything together. So we have 12 divided by 1,000 times 0.70 divided by 2. Let me see what else I have. And then divided by 0.10 times 1,000. Okay, so 42 milliliters of barium hydroxide will completely neutralize this reaction. So that's something to do. And then what else did they want? Sorry. So 42 milliliters of barium hydroxide. indicating the shape of that and approximate equivalence point. Okay, so since they're asking for an approximate value for your pH, we're not actually going to find the exact pH just because they actually didn't give us enough information. But what I'm going to do is let's draw that out. So now that we know that this is the equivalence point, what this graph will look like is whenever we're titrating, or really whenever we have a weak acid and we're titrating that with a strong base. And these are ones to know, by the way, right? We know a strong base has that OH. It also is going to have, this is a trick for you guys. So for a strong base, you know it's a strong base because it starts off with the first two groups. So those metals, anything combined with either group 1 or group 2, and that's then combined with OH, that's going to be a strong base no matter what. Okay, so that's just something to help you with memorizing. And then since this is a strong base with a weak acid, how this curve is going to look is here we're going to have the milliliters of our base, okay? And then on the other side, or on the y-axis, we'll have the pH. So essentially what your curve is going to look like is we're going to start at not too low of a pH just because it's a weak acid. So it's not going to start off at like 0 or 1. It could start off at like 3. And then from here, it's going to look something like that, where the main thing to look at for your equivalence point with your pH, and by the way, we figured out that our equivalence point was 42 milliliters, which is what I'm going to put here. And where this pH is roughly going to be, it's going to be around 8. So when you have a strong acid, strong base, your pH at equivalence point is 7 because it's completely neutral. However, when it's a weak acid or a strong base, it's a little bit more basic because we have a strong base, which means it's going to be more basic, right? So then that's why our pH would have been roughly 8. Okay, so any single time we have a weak acid, strong base, your pH is greater than 7. So that's where our equivalence point would have been. Okay, and that's where the pH would have been. It really is close to 8. All right, so that pretty much answers 2 questions. So let's move on to another question. Okay, let's see. We have, what mass of lithium phosphate would you need to make, and let me start writing this. So we're looking for our mass of lithium. So lithium has a +1 charge, phosphate is PO43-. This would have been, this 3 is going to go down. So this is really what we have. So we're looking for, mass really just refers to grams. So okay, we're looking for the grams of lithium phosphate, and let's see what we're given. So we're given 2.5 liters of 1.06 molar solution of lithium phosphate solution. Okay. So once again, we're going to use molarity as a conversion factor. And where I'm going to start is I'm going to start off with the liters of lithium phosphate that they gave us. Then I'm going to convert this to moles of, once again, lithium phosphate using the molarity. And then lastly, what I'll do is I can convert this to grams using the molar mass found on our periodic table by adding them all up. So then these are pretty much the 3 steps we're going to take here. So let's start. So I'll start with the 2.5 liters of lithium phosphate, and then I'm going to multiply this by the molarity. So remember, molarity can be broken down to moles divided by liters. That's exactly what I'm going to do here, where there's 1 liter on the bottom and the 1.06 moles goes on top because we want these liters and liters to cancel. And then from here, I'm at moles of lithium phosphate. So then now I'm going to figure out the molar mass of lithium phosphate. So let's do that together because we will have 1 mole of lithium phosphate on the bottom, and we'll put whatever mass we find in a second on top. Okay, so let's go back to our periodic table and then figure out what we have. So lithium has a mass of 6.94, and I'm going to multiply that by 3 since there are 3 of them. Okay, and let's do that together. So we'll see how much we have. So 6.94 times 3, that gives us 20.82. And then phosphate has a mass of 30.97. We'll add those up in a second. And then oxygen has a mass of 16. And then I'll multiply that by 4 since there are 4 of them, giving us 64. We'll add all of these values together and we'll put that on top. So 64 plus 20.82 plus the 30.97, and that gives us 115.79. Okay. Last step here is to multiply everything straight across. So multiplying the 2.5 times that 1.06 and then times this value. And then we'll finally get our answer. So multiplying all those values together, we will get 306.84 grams of lithium phosphate. Let's double check our sig figs. And we were initially given, to the lowest amount of sig figs we were given were just 2. So I'm going to stop right here. This would have been 307, really rounding up. Last step here, if your professor is really picky with sig figs, which most of them are, is I'm going to change this to scientific notation just so I do have only 2 sig figs. So moving this over 1, 2, this would have been 3.07 times 10 to the second grams of lithium phosphate. Last step, I'm going to round up again, where this would have really been 3.1 times 10 to the second power grams of lithium phosphate. We're finally done. So that's the amount of sig figs you will see, and that's the mass. All right. Next question. I have Trey saying, do you have any tips or tricks for the AP Chem exam tomorrow? Okay, so I know a lot of you guys are actually taking your AP exams tomorrow, so good luck with that, absolutely. My main tip is know how to use the formulas. And I know that sounds ridiculous, but a lot of times, like, what I really recommend doing is having all the formulas that you have really ever learned with chemistry in your class and just looking at them and saying, do I know how to apply this formula? When do I use this formula versus the other? And knowing those, differences and variations of the formulas are going to help you so much. So that's the main thing. I mean, the nice thing about chemistry is it is a lot of formulas. Of course, there are so many exceptions to the rule. So what I recommend doing is, yes, write down all those formulas that you have. By the way, I do have a formula sheet that I give for free. So if you check this description box of this actually live Q&A, you can find the formula sheet. So that kind of cuts your studying in half right there. And then you can print that out and really just look at it as, which formulas are going to be on the exam, like which ones did you guys actually cover? And then from there, what I also recommend doing is actually writing the exceptions. So a lot of times with AP exams, they love to throw in those exceptions. So like, let's say, an exception could be when the octet rule is actually going to be used, or when it's an exception to the octet rule, when it's an exception to the electron configuration, the typical values of it. So like that's something to look at and like write down for all the different sections, knowing how to use the formula and knowing the exceptions to pretty much the rules. Okay, so that should help. And I am answering one question per person. So and Julie, I really answered one of them. Okay, so I'm going to answer another one. Let's see. Amanda. Okay. And let's see what you have. Okay. So Amanda asks, in a reaction in a calorimeter, the temperature of 32.0 grams of water increases. And let's start writing this down. So in a reaction, we have a temperature. Oh, actually, we have our grams first. So 32.0 grams of water increases from, and this is our change in temperature. So we're going to start off with our initial temperature at 19.50 degrees Celsius. And then our second temperature, our final temperature, is 22.83 degrees Celsius. How much heat is absorbed by the water? Okay. In a calorimeter, the temperature of that amount of grams. Okay, so what I'm going to use right now is Q is equal to MCAT. So this is the formula you're going to see. Sometimes you could also see it without the S. I've also seen it this way. Okay, both mean the same thing. So what they didn't include was your specific heat capacity of water. So that's something to definitely know. Your specific heat capacity for water is 4.184 joules divided by grams Celsius. So for calorimetry, we're not going to change our temperature to Kelvin. We're going to leave it in Celsius. The reason why we're doing that is because our specific heat capacity is in Celsius already. So all I have to do at this point is to figure out the change in temperature, then plug it all into the formula. So for our change in temperature, it's always final minus initial. So that would have been 22.83 minus 19.50. We'll figure out what our temperature change is. So 22.83 minus 19.50, and that gives us 3.33 degrees Celsius. That's our change in temperature that we're going to plug in. All right. So at this point, really just plug everything in and let's see what we get. So Q is equal to our mass of water was 32.0 grams. Our specific heat capacity, now that we know that, is 4.184. And that's joules per grams Celsius. And I'll multiply by our change in temperature. So this would have been 3.33 degrees Celsius. You'll notice that your grams would cancel Celsius and Celsius, and we're left with joules, which is what heat is measured in. Specifically, heat prefers to be in kilojoules, or at least that's what I see most professors or teachers prefer, which we can convert at the end. So I'm going to multiply everything together. So 3.33 times 4.184 times 32, and that would have given us 445.8 joules. It is positive because they're telling us that heat is being absorbed. Whenever heat is absorbed, it's positive, and whenever heat is being released, it's negative. Okay, so last thing, since we had only 3 sig figs with this first value, I'm just going to round up. So rounding up, this would have been 446 joules. That would have been our heat absorbed, and I actually feel like joules should have been fine. They didn't specify what they wanted the unit to be, so that should be fine. But yeah, Amanda, that would be it. And Stevie is asking another type of calorimetry question. Let's see what we got. So what temperature will a 453.6 gram piece of lead, or PB, reach if its initial temperature, so we know the initial temperature, I think I really know what type of question this is, the initial temperature of lead is going to be 25 degrees Celsius, and that amount of energy are being added. Okay, so we know, oh, I see, okay. I thought we were going somewhere else with this, but we're not. And we're looking for the final temperature. We'll reach its initial temperature. It's not being dropped in anything. Nope. Okay. So we're looking for final temperature in Celsius. So let me plug in what else we have. So we also have Q. So Q, or energy, is this amount. And we're also given our specific heat capacity, or specific heat, which is 0.159 joules per gram Celsius. Yeah, the specific heat capacity. We're going to use the exact same formula, just use it a tiny bit differently. So we're still going to use Q is equal to MCAT. And then the only difference here is we don't know our change in temperature. So I'm going to expand this formula just a little bit. And I want you to think of it as, and actually even before I do that, let's just start off with expanding everything. Yeah. Let's expand it. I think that'll be the easiest way. So expanding all of this, our change in temperature, remember, is really T final minus T initial. So T final minus T initial. And what we're going to do now is just plug everything in. So we're actually given our Q, which is this value. And then we're given our mass, so 453.6 grams. We're given our specific heat capacity, which is 0.159 joules per gram Celsius. And we don't know our final temperature. That's what we're looking for. But we do know our initial temperature, which was that 25 degrees Celsius. Okay, so I'm not going to distribute anything. Instead, what I'm going to do is I'm actually going to multiply these two together. So let's figure that out first. So multiplying 453.6 times 0.159. This would give us 72.12. Let's see. Let me look at the units real quick. So our grams and grams would cancel, so we would be left with joules per Celsius. Okay, I'm still not going to distribute anything just yet, or whatsoever. And the reason is because I could actually divide that 72.12 over to the opposite side. So 72.12 joules Celsius. I'll divide those two values. This is going to cancel. Our joules and our joules will cancel as well. Let's divide those two values and see what we get. All right, we'll see what we get from this. This gives us 202.4 degrees Celsius. T final minus, and then now I'm going to drop those parentheses. We don't need them anymore. And then lastly, just add over that 25 degrees Celsius, and that's our final answer. So T final is going to equal 227.4 degrees Celsius. Let's go back to looking at what you have. So the lowest amount of sig figs you have is 2. So I'm going to round to really just 2 sig figs. I could round really up and just see that this could have been 230 degrees Celsius. Okay, because remember, it's just these two sig figs that count. That 0 at the end does not, since there is no decimal place. So this would have been T final, and we are done. Okay. This is the question I was thinking of. Okay. So more calorimetry questions. John asks, if you drop a 50.0 gram piece of metal, all right, so we'll say this is our metal, with a temperature of, I'm assuming this is our initial temperature, of 100 degrees Celsius, into 100 milliliters of water, and that's at an initial temperature of 25 degrees Celsius, or room temperature. What is the specific heat capacity if the final temperature of both the metal and the water, so okay, our final temperature is going to be the same, is 30 degrees Celsius, and we're looking for the specific heat capacity of the metal, I'm assuming, yeah. Okay. So the information that they expected you to know is, 1, the density of water, as well as the specific heat capacity of water, which I'll tell you, but those are definitely ones to know. But we're looking for the specific heat capacity of the metal, which we'll get to. Okay. So the main one to remember for water, for your specific heat capacity, is going to be that 4.184 joules per grams Celsius again. All right, that's one to definitely know. Next, your density of water is just 1. So 1 grams per milliliter. And then what we want to do is we're going to build this formula. So we're going to have Q of our metal is going to equal negative Q of our water. And then I'm going to expand this a bit further. And what this is going to look like, this is going to be the mass of our metal times the specific heat capacity of our metal, which is what we're looking for, times our change, so T final minus T initial of the metal, and then that's going to equal the negative mass of our water, which we will have to use the density to figure that out, times our specific heat capacity of water, which was that 4.184, and then once again, here, I'm going to kind of separate all these. And then our change in temperature once more. Okay. So before I start plugging anything else in, let's just convert that milliliters to grams. And I know it's really the same thing, but I'm going to show it regardless. So showing 100.0 milliliters of water, using its density just to change it to grams. So there's 1.00 grams of water per every 1 milliliter. I know when we multiply, it's going to give us the same exact thing, but some professors are picky and they want to know how you change that. All right, so that's how we change it to grams. And then now I'm really just going to plug everything into that large formula and then just solve for our specific heat capacity of the metal. So our mass of our metal was 453.6 grams. We're looking for our specific heat of the metal, so I'm just going to leave that. And then our final temperature, we said it was 30 degrees Celsius minus our initial temperature of the metal was, let's see, 25. Okay. And then next, I'm going to keep plugging everything in. We said that our mass that we just converted was 100 grams for water. And then our specific heat capacity for water is 4.184 joules per grams Celsius. And then our final temperature we said was 30. Our initial temperature for the water, oh, I'm sorry, this one was 25. The initial temperature for the metal was 100. I'm like, it should have been hotter. Yeah, there we go. Okay. Right, make sure if I read everything right. If it's an initial temperature of, looking at the wrong one, with a temperature, there's so many of you guys, temperature, there it is. Okay, yeah, so this is fine. Okay, what I'm going to do now is a bunch of math. Okay, so I'm going to start off with the right-hand side, and I'll do what's in parentheses first. So just subtracting those two values, that would have been 5 degrees Celsius. Now I'll multiply that 5 times 100 times that 4.184 times a -1. So multiplying all those two together, let's see what we get. So on the right side, we'll get -2092, and then really everything, this is going to be left in a joules, but since we're looking for, and actually I'll show it, this would have been left with joules because our grams and our grams would cancel, and our Celsius would cancel, and we're left with joules. So next, I'm going to multiply what I can on the other side. But before I do anything, I'm going to do what's in parentheses again. 30 minus 100 is -70 degrees Celsius. And then I'm going to bring these two, I'm actually going to multiply these two values together. And let's see what we get there. So -70 times 453.6 gives us this large value. And we still have our specific heat capacity of our metal. I'm going to set that equal to the other part of this. And then the last step of this is really just to divide. You'll notice your units. Let me go back to my units. Your units would have been grams times Celsius. And that's what's going to help determine or actually give us the correct units for our heat capacity. So last step is I'm going to divide all of this over. Dividing all of this over. And let's see what we get. So these negatives will cancel, right? It's going to turn positive. And let me divide those two. So 2092 divided by 31752. This would give us 0.066 joules per grams Celsius, and that is the correct specific heat capacity. All right, so that's exactly what you would get for that type of question. Okay, let's move on to the next question. And next question is from Tammy. Okay, so this looks more like biochem with this type of question, but we're looking at ADP, and we have phosphoric acid. We're given 38 kilojoules of ATP plus water. All right, let's see what this question is asking. So if we have 995 kilojoules of energy are used in a reaction, how many moles of ATP are produced? What is the mass of phosphoric acid if 155 kilojoules of heat is added to the system? Okay, so let's start with the first question. They're giving us initially 995 kilojoules of energy was used in this reaction. The only thing I'm kind of curious on with this question was that 38 kilojoules yields ATP. I'm assuming that's going to be used as your moles. Yeah, why else would it be there? It's just kind of strange how it doesn't really look like a typical mole to mole ratio, which is totally fine. But that's what I'm going to use. So what I'm going to start off with is I'm going to start off with that that? 995 kilojoules of energy, since that's what they give us. And then what I'm going to do is I'm going to multiply this by the amount of kilojoules we have for every 1 ATP, since that's all they're giving us. So they're asking for how many moles of ATP. What I'm going to do is I'm going to put 1 mole of ATP, just because that's what was given in the formula. And then on the bottom is that 38 kilojoules. And that's it. That's all we would use, since they're giving us the energy, essentially. Yeah, that's actually the first question completely. We're just going to divide those two together. We'll see what we get. This would have been 26.2 moles of ATP. And then that would be the first part. What's the second part? What is the mass of phosphoric acid if 155 kilojoules of heat is added to the system? Okay, so if I started off with 155 kilojoules is added to the system, that's our reaction. Q of our system is equal to, I'm just thinking, would it be negative? I will use the molar mass of phosphoric acid. Let me see what else I can use with that. 995 energy of the entire reaction. What is, now we're changing it. Oh, I see. Now we're changing it. And then we just have 1 mole of phosphoric acid, and I'll change that to mass. Yep. Okay, so what I'm going to do is think of this as being per every 1 mole, and then I'm going to multiply this by the amount, and I'm still considering, because that just looks so strange, the 38 kilojoules per ATP. I'm going to go back on what I was saying. Sorry. Thinking about this one. It's just written kind of weird. I'm going to go back to that 995 kilojoules for the reaction that they gave us. It's added to the heat. What is the mass of phosphoric acid if that of heat is added to the system versus that being given as the reaction? What I'm thinking of, by the way, and this is why my brain's like, do we do this? Do we not? Is actually Q of your system is equal to the negative Q of your surroundings. And then, however, they don't really tell us too much of this question. And then, well, Q of your reaction is then the negative Q of your calorimeter, but it's different in this question. So what I'm going to go with this question, what I'm thinking of, is I'm going to stick to that 155 kilojoules because they are changing it. They're saying that that's just of heat of our system. I'm going to keep going with my thought. This would have been per every 1 mole of phosphoric acid, since there's only 1 mole of phosphoric acid, and then I'm going to multiply that by the mass of phosphoric acid, and that's going to give me the grams. So the molar mass. So then, oh, I see. I flipped this. Let me flip this. It's just so they can cancel. I'm going to flip these just so I can have that molar mass cancel out. So this would have been 155 kilojoules, and reaction, that's going to cancel. That's going to be that. I'm still debating on this question. Sorry, guys. The reason is because then our kilojoules has to cancel, and that's not going to. I know I'm missing one little piece of information. So if I were to have, one sec, let me think about this. I know this is going to be our grams of phosphoric acid, and then 1 mole of phosphoric acid. I'm working my way backwards, and then 1 mole of phosphoric acid based on the mole to mole ratio. And then I would have to have some sort of heat, but I need heat to cancel. And actually, I don't. And that should have been 995. Okay. Okay, I see it. I'm going to actually start off with the 155 kilojoules, just because that's what they're telling us to start off with the second part of this question. They're stating, what is the mass of phosphoric acid if we're given that 155 kilojoules of heat? So this already is our heat. What they're telling us, though, is the energy that was initially provided of the reaction was 995 kilojoules per every mole, since that's talking about the entire reaction. So that's why I'm using it as a conversion factor right here, and I'm allowed to flip it around. So what I'm going to do is I'm going to multiply. I'm actually going to do this exact setup, multiplying that 155 kilojoules times the kilojoules 995. And then now what I'm going to do is I'm going to get the molar mass of phosphoric acid. So hydrogen has a mass of 1.01 times 3. This would have been 3.03. And then phosphorus has a mass of 30.97. Oxygen, 16 times that 4, which is 64. Add everything together, and we'll see what mass we get there. So 3.03 plus 64 plus 30.97, and that gives us 98. And then we'll multiply straight across. So multiplying these two together and dividing by this bottom value. So multiplying straight across, dividing by that bottom value, we will get 15.3 grams of phosphoric acid. Okay, that would be it for that part. All right, let me see if I can answer another question. Believe this is from A. Let's see. A 7.51 gram sample of this is placed in 100 grams of water in a calorimeter. The material dissolves in the water and the temperature of the water drops from 24.8 degrees Celsius to 19 degrees Celsius. What am I finding? How many moles of that are involved in the process, and what is the change in enthalpy? Okay. I'm looking for the amount of moles. So I'm most likely going to find amount of heat, then that would have been, yep. So since we're eventually going to find our enthalpy, the formula that you need to know is that Q of our reaction divided by moles is essentially our change in enthalpy. So what I need to figure out first is I need to figure out what our Q is. And before I even do so, let's just figure out, here, they gave me, a sample is placed into water in a calorimeter, and the material dissolves in the water and the temperature of that drops. Okay, so this is really similar to that other one that we were doing where, like, let's say we had metal, the Q of our metal is equal to the negative Q of our water. Same concept here, except we have some sort of sample, and then this would have been negative Q of our calorimeter. So essentially what you could have even thought of, and let's see, yeah. So this is essentially what I'm going to do. I'm going to expand this formula again, and then I have to figure out what part of this, though, because we're not given the specific heat capacity of that. Actually, no, it's not even necessary, come to think of it. There's 100 grams of water. I don't see how they're relevant to this. So the material dissolves in the water and the temperature of the water. Got it. We're adding those two together. How many moles of that are involved in the process? And what is that? Okay. Thinking about this question. This is what we're using. All right, so since we're looking for Q of our reaction, that really means we're going to start off with the Q of our calorimeter. Because this is dropped in a calorimeter, that's what we have to find first, and then we'll make it negative at the end. So what I'm going to do is the Q of our calorimeter is going to equal the mass and our specific heat capacity and our change in, actually, not our specific heat capacity, not our mass. Should have been this. We're looking for our moles. I'm just thinking this is an interesting question. The other thing I can do, I can add those two together. They don't give me the specific heat capacity, which is what's weird to me. And I can figure out the change in temperature. Let me figure out the change in temperature and think of it. So AA or whoever asked this question, did they give you the specific heat capacity of that sample? Because that's the missing piece of information that I need. If not, I'll see what I can do, but that is something I needed. All right, so I'm going to do final minus initial for our temperature. Let's see what that gives us. 19 minus 24.8. That's negative 5.8 degrees Celsius. All right, yeah, and the specific heat capacity, if they gave it to you. If not, then I'm just assuming they're using water, and that's known. And then our change in temperature is that. The other thing that I can think of with this question, since they're asking for the amount of moles, is I can figure out what Q is, and actually they're not giving me that. I can figure out what Q is. There's a lot of unknowns to this question, just thinking about it. I know how to figure out the enthalpy. That's not a problem. We don't know the amount of moles. I can change that. I mean, I can convert it. Then I can figure out how many, what's our Q of that. It's actually exactly what I'm going to do. Okay, answered my own question. Hello. So, no, they didn't. Okay, no, I figured. It's fine. They don't always provide everything necessary, unfortunately. Trust me, as a tutor, you learn that. So what I'm actually going to do first off is, since they're giving us the sample or the grams, I'm going to change that to moles just because they're asking how many moles are involved in this process. The other thing I can think of is actually building an equation since we are given water. And let's see what that would have even given us. Goodness. So that would have been a base. That would have canceled. Let me see if I can find the balance equation because I know we're pretty much out of time already. One sec as I do this. Okay. I don't even see them doing that to you guys either. All right, that's fine. I'm gonna go with my initial thought. I would have literally just converted this to moles just because they don't give us a specific heat capacity, so I don't think that they want that part, as strange as that is, which they should have. I'm gonna convert this to moles, so that's my initial thought with the first question, and then figure out the change in enthalpy. This is really what we're gonna do here. So Q of that would have plugged in. The material dissolves in the water and the temperature, so I add those together, and that would have been our specific heat capacity. Yeah, okay. Then that would have been our specific heat capacity. I can then figure that out. It's exactly what I'm going to do. I'm going to change this to moles. So changing this to moles, using the molar mass like we typically would. All right. And let's figure that out. So N would have been, we have two N's, so really 28 grams. And then H, since there are four of them, so 1.01 times 4, so 4.04. Oxygen, there are 3, so 3 times 16, giving us 48. Add those two to get all those three actually together, 4.04 plus 48 plus 28. This gives us 80.04. Divide those two values. That's going to give you the amount of moles, and then we'll use this in a second. So 7.51 divided by 80.04. That's 0.094 moles. So that's going to be the first part. Now, what we're going to do next is, because they're telling us that the material dissolves in the water, that essentially tells us that our mass is actually going to be whatever that sample was, the amount of grams, plus our mass of our water. So I'm going to add those two together. So adding the masses together, so really 7.51 grams plus the 100 grams, that's going to give us 107.51 grams. And then from here, I'm going to plug this in. So this is going to be Q of our calorimeter, or actually our reaction, is going to be equal to 107.51 grams. That's our mass. Our specific heat capacity, since they're not giving you anything, I can assume that it's just for water. So this is 4.184 joules per grams Celsius. So that's what I have to put here. And then our change in temperature that we found previously, let's see what we found before. That was negative 5.8. Negative 5.8 degrees Celsius. That'll give us joules and pretty much our heat of our reaction. So let me see what that gives us. So 4.184 times negative 5.8 times 107.51. And that's negative 2608.9 joules. And then since they're asking for our change in enthalpy, what I'm going to do now is just divide this by the amount of moles that we found initially. So the moles of whatever sample we had, which we said to be this value of 0.094. 0.094. We'll divide those two values together, and then that'll give us our answer. And let's see. So dividing these two numbers, negative 27754 joules per mole. That would have been our change in enthalpy. And let me just make sure one thing, that our sign is negative. So we placed a sample in the water in a calorimeter. Material dissolves and the water drop. Yeah, we're good. So that would have been it for this question. The main thing is to just figure out the amount of moles here that we did before. And then since they didn't give us our specific heat capacity of that sample, I could assume that they're just using water's specific heat capacity. Okay, so then that would have been this part of it. So this is our final answer. Okay, guys. So that concludes today's Q&A. Thank you for being here. Goodness, we went through a lot of questions. That's awesome. And definitely, quick little note for those who joined a little bit later is something that I'm really hoping to accomplish or get to this at the end of this semester is to reach 10,000 subscribers. And if you guys help me out with that, so share my videos, tell your classmates and anyone or teachers, anyone that can benefit from chemistry help, then what I plan to do is doing an 8-hour live Q&A. So if we make that 10,000 subscriber goal, I will do an 8-hour live Q&A to help you guys, because I know 1 hour just isn't enough. All right. So that is today's Q&A. So I'll see you guys in the next Q&A next Sunday. If you guys really want your answer or really want your questions to be answered, make sure to be on time. That guarantees or really, I will answer the ones in order. But yeah, all right, guys, I'll see you, and I hope you have a wonderful Sunday. See you guys.